Good afternoon, ladies and gentlemen, and welcome to today's presentation. Certainly appreciate the time out of your afternoon to join us. My name is William Lusk, and I am with OCEANS LLC. Just a very quick introduction as far as who OCEANS LLC is. We are a service-disabled, veteran-owned small business that is based out of Jacksonville, Florida. We provide consultation services to government and commercial clients in the design, management, and implementation of effective, sustainable, multi-domain security and information sharing solutions. OCEANS brings together decades of experience in improving maritime interdiction, naval architecture, survivability analysis, port and border maritime security systems, piracy and terrorism mitigation, enterprise architecture, software development, systems lifecycle, systems engineering, training, exercise, evaluation, research, and development. So, what I'm going to do is give a very brief introduction to Mr. Eddie Hughes, who is our guest speaker for today. Who is our radar-based drone detection and mitigation expert. Mr. Eddie Hughes is the president and founder of DMT, and he has 35 years of radar design, builds and analysis, and algorithm development. He has degrees in physics, mathematics, and completed studies in oceanography, astrodynamics, and engineering. He has served as the radar SME for the Ballistic Missile Defense Agency, taught radar classes for stealth technology in the U.S. Navy, and he started DMT in 2002 and expanded its reach globally ever since then in just a few short years. Due to the overwhelming demand over the past few years from commercial and government clients, Mr. Hughes from DMT has expanded R&D in his commercial radars to now include the need for drone detection, tracking, and analyses. My function for today's webinar is to act as the facilitator. I will be muting everyone's microphones to ensure that our presenter for today is heard very clear. I will also be monitoring today's chat function, so if there are any questions in the middle of the presentation, feel free to shoot me, the presenter, a question, and I'll be more than happy to make a note of it and get to that in the Q&A. If for some reason we do have a technical glitch and you're forced to log off for some reason, fret not, we will be recording today's presentation and putting it on our website, which is www.oceansllc.com. So, with all of the boring stuff out of the way, let's take it over to our main speaker of the day, Mr. Eddie Hughes, and you, sir, now have the controls.
Hey, well, thank you very much, Will, for the intro, and thanks to OCEANS for the speaking invitation today, and thanks for all of you for logging in today to listen to the presentation. I'm going to keep today on the rather light side of technical, but would be more than happy to get in any technical discussions. Just as Will said, just let him know on the chat side, and we can cover those things later during the Q&A session. Today, again, I'm going to be talking about drone detection using radar, and one of the first things that people ask me is, why use radar for drone detection? What is the benefits for using radar for drone tracking and detection? Well, the first thing, it's probably the strength of radar overall for all applications in any security mode, whether it's vehicles, whether or not it's boats, airplanes, whatever. Radar is known for the ability to search very large volumes rapidly. So that's the one thing that you need for drones and for drone detection is the ability to rapidly detect and track. Many people think of scenarios where the drone is flying in from some distance way off of my property perimeter, and they fly into my site and try to either look at things or do harm. In the case of many kinds of drone scenarios, oftentimes the drone operator may carry that drone in a backpack and pop up very close to your site. So you may not get that luxury of a very long tracking distance on them. So the one thing you want to be able to do is to track that drone as soon as you can possibly get him under track. Radar is great for that. Better than optical systems and many of the other systems out there. And although there are other methods of detecting drones, such as RFI, monitoring the communication between the drone handset from the operator's perspective and the actual communication from the drone itself. Those things only work as long as there are communication between those two. If the drone is autonomous, flying by waypoints, there will be no communications. So radar in those instances is the only way to detect, especially for any distances. Acoustic sensors are also often used as well for the detection. The actual detecting the sound that's given off by the props can be quite unique. Many of you may have been outdoors and hear a drone coming up on you. That drone sound is very unique and can be differentiated. The only problem is wind can greatly affect the range of those types of systems, as well as the range in which, not only the range, but the actual ability to differentiate between those drones. So the one thing that's nice about radar is its ability to precisely track drones, even when there's no operator, even in the wind, even when the clutter is bad. And a real example of that too is for instance, wanting to know where did the drone take off from and where did the drone land. Those are two important things that you would like to know when you're monitoring for drones. And radar is very good at being able to provide you those locations. The other thing that's great for drones detection is the fact that if you've got the right frequency and use of Doppler processing, the one thing that radar is great at is being able to detect in all kinds of weather. You say, well, drones don't fly in the rain, but there could be rain between you and the drone. It may be flying, if you're in Florida, you may be flying in a sunny day, your drone, and there's a cloudburst between you and the sensor that's trying to track you. Radar can see through that rain, especially if it's, again, the right frequency and the use of Doppler. Also, if there's anything going on at your facility, like you have smokestacks or there's a fire or whatever, radar can see through that to be able to allow you to detect. It also is great at being able to pick out drones in a clutter-rich environment. Clutter means anything you don't want to see. That's like grass, trees blowing, all those things. Doppler allows you to be able to remove those items from your environment and be able to only see those things of interest like a drone. So now we know why you might want to use a radar. What are the things that a radar actually tries to detect out there? The main thing that every radar out there that's ever been made tries to do, and that is to measure signal strength of the objects at both range and bearing. So every radar that's ever been invented pretty much can do this. They can measure that. Perhaps even many of you don't know that even your police radar has the capability of doing it. They just are too inexpensive to be able to give the range. But in any case, the signal magnitude is one of the things that's measured. Now, signal magnitude is really a measure of the radar cross-section of an object. Radar cross-section is very similar to optical cross-section. When I say optical cross-section, I mean how big is that object in square meters? For instance, if you look at a person and that person is 2 meters tall by 0.6 meters wide, their optical cross-section is 1.2 meters squared. So in the case of a radar, it also sees the object at that size. The problem is that the cross-section also accounts for the reflectivity of that object. The object itself, like a human, is somewhat absorptive. So it can absorb some of the RF energy that's being radiated. And like this also is the case for drones. A drone is made of a lot of plastic. Even the blades are plastic. So in the case of those objects, their radar cross-section is much smaller than the optical cross-section. And the range of a radar is directly affected by the radar cross-section. Its range is directly affected by that. Now, if the radar is a Doppler radar, it has the ability to measure Doppler, then you also can be able to monitor all of the velocities associated with that object. You say, well, what good is that? Well, one of the things you can do by measuring velocity is to say, I want to see only those things going toward me at 5 miles per hour or greater. And what that will do for you, for instance, would remove tree waving, grass waving, water motion, all of that would be removed, and you would only see those things going 5 miles per hour or greater, which might be that drone approaching you. So it's very good at being able to measure speed, and not just the speed toward me, all the speeds present. So for instance, one of the things you may hear out there today for drone detection is the use of micro Doppler. And what that is actually looking at the things that are moving on the object, not just its speed toward me or away from me, but the speed of the items on it, like the props spinning or the shafts of the motor spinning. All of those things are possible to be measured and can differentiate one drone from another, or say one drone from a bird. So what can affect the actual overall RCS of a drone? I have here some images. Now, some of the images I have here were obtained from the University of Texas in Austin. They made a bunch of measurements under, I think it was actually funded under the government, to measure the RCS of many types of drones. And this is some of the types of things they did in terms of measuring drones. One of the things they looked at and said, if I have a drone and its blades are not spinning, or its blades are spinning, what does it look different to a radar? And one of the things they found out was no. Now you say, why doesn't it look different in radar cross-section? The reason for it is because the blades are plastic. And plastic, at least the plastic used in drones, is pretty much transparent to radar. So those blades can spin all day long and we're not going to see too much of them. Now, if you have Doppler processing, what DMT's found is you can see other things, maybe the shaft of that motor spinning, which is made of metal. The other thing they found was that with frequency mattered a whole lot. What was the radar transmitting? What was the frequency of that radar? And this is sometimes in the United States determined in part by the FCC. If you want to sell this thing commercially, you may have to be restricted by the FCC. But the other thing is that for those bands that you can transmit in, they found that the higher the frequency, especially when you got up into the X band and higher, you had much better, larger radar cross-section measurements from drones. What this means is like, for instance, in this case here, the difference between a low frequency radar and a high frequency radar is 10 times. It's 10 times the difference in radar cross-section. And when you have a 10 times difference in radar cross-section, it relates to about a 2 times range improvement. So for that frequency, I could see that drone at X band or higher more than 2 times further than a radar that's, say, S or C band. Okay, the next one thing that can affect RCS is the polarization. I don't know if many of you know about polarization, but your glasses, if you have sunglasses that are polarized sunglasses, the way they work is because it restricts the sun's light into one plane. So light normally reflects off of everything, but the polarized lenses keeps the light wave aligned in only one plane, and that takes away a lot of glare and strength. Well, in radar, we use polarization to amplify certain objects. For instance, if a telephone pole is really long, so if you use vertical polarization, you'll see a telephone pole much better than if you used horizontal polarization. Conversely, if you had a ship is really wide, right? It sits on the water. Its longest dimensions is in azimuth, in the horizon. So you would use horizontal polarization to see a ship better. So in the case of drones, they found that certain polarizations brought out certain signatures more. Like, for instance, drone batteries seem to be much easier to be detected in vertical polarization. So, some of the drones that fly really long distances and can stay up a really long time, well, the reason why they do that is because they're either lightweight or they have a big battery. So if they have a big battery, then the vertical polarization would be the better way or better polarization to see them. Also, the other thing is the motors. The motors were easier to be seen in horizontal polarization. Now, so that's what you say, well, what does that mean? For instance, if it's big drones have bigger motors because they're carrying bigger payloads. So in those cases, the bigger drones would be easier seen, their motors at least would be, if you're looking in H-pole. Also, of course, they found a lot of differences in, of course, what you put on an object. If you put a camera versus not a camera, they found differences in the radar cross-section, but more importantly, what it looks like to the radar changes with those objects on there. So again, a lot of very interesting measurements they made. Of course, when you change the type of drone that you have, you're going to get a different Doppler or RCS signature. And you can use these kind of signatures to help you classify the objects that you see. Now, I know I didn't describe much about these graphs that you're seeing. What you're seeing really, this is called an ISAR image. It's an accumulation of measurements made by the radar. It's not just a snapshot. And what we have here overlaid on that is the orientation of the drone for that particular image. So we see in this case in an azimuth scan, this would be what the drone would look like if it was flying overhead of me. And then to the right-hand side is an elevation scan. This is what if you were looking at a drone flying away from you, far away from you, for instance, you would see this kind of signature. So these are, again, computed with using a number of looks at that drone, accumulating that image, and creating this nice, what's called ISAR image, which stands for Inverse Synthetic Aperture Radar Image. So nothing that you need to remember, just one of those many features that's good with for the drone. And again, if I have the movie here, if I could switch to this screen. Oh wait, I can switch screens. Haha. Yay.
Yes.
Okay, so now I can go and see the right image here. So there is a 3D image of a drone flying directly over my head. So that would be what it would look like if you took all the cuts of RCS of a drone as it's flying overhead. That's what it looks like to the radar. Now, you can take these images and use them to be able to differentiate a drone from a bird, for instance, or something else like that. So again, a really great feature is the RCS. Let's go back up to the next slide here. Sorry for my technical difficulties. Okay, so the things to consider about drone detection when you have a radar. There are a number of things that the radars that you look at should be considering when they design the system. One is the transmitted frequency. We know that in order to see a drone better, we just showed you in some of those graphs that you need a higher frequency. DMT is found, for instance, at X-band makes a great transmitted frequency for drones. Doppler processing. Doppler processing is essential of getting rid of the environment. You don't want to see trees blowing. You don't want to see telephone poles, light lines, or anything else. You want to just see the actual drone itself, and that definitely helps you. Also, microdoppler will allow you to help you classify against birds, for instance, or other objects that may look similar. Scan volume is very important. You want to be able to have a radar that's not, the typical shipboard radar will not work for drones. It has got two, it has basically it's called a 2D radar. It's not a 3D radar. You need to be able to scan in elevation to be able to see that drone as it approaches you. Range for all the radar systems should be more than twice the range of what you would be looking for a human. For instance, if you see somebody who has a radar that says they can see a human at 1 mile away, well, if you want to buy a drone radar, that drone radar needs to be able to be at least 2 times that range. So if you said I want to see, if I want to see a drone at 1 mile, then you need to have a radar that sees a human at 2 miles. So it's basically takes twice as much effort or more to see a drone than it is a human. The other thing to consider too is radomes. Some of the drone detection systems out there have no radomes, but if you're an operator, you can see where the radar is pointing without a radome. Radome is a cover that actually fits over the radar. It protects it against the elements, but also keeps you from seeing where it's pointed. It's a really nice thing to think about when you're looking at radars for it. And probably one of the most important things is the communication of that data to other counter-drone systems. You want to make sure that you can push that data out to any operator, but you also want to be able to do things like, say, point a camera or point a jammer, something like that. So that should be, the system should be capable of having a very easy to use either API or communication system to be able to get that data out there. I wanted to put this plot up here because this sort of tells you a little bit about the part with volume or 3D scanning. What I have here is the look-up angle for a drone that's flying 1,000 feet in the air, and your radar is on the ground. This is how much you would have to tilt your radar up to look at the drone as it approaches you. So way out in the say beyond 5 kilometers, the drone is pretty much on the horizon. If you're looking out toward the horizon, you'll see it no problem. But as the drone approaches, by the time you're at 1,600 meters away, which is exactly 1 mile, you're going to have to already be pointing your radar up 10 degrees. By the time it's at 500 meters, you're now having to tilt the radar up over 30 degrees. And as it approaches you, the look-up angle is extreme. It can become to the point where your radar is basically having to look straight up. So you really want to make sure you have the ability to look in 3D with your radar systems. Okay, the other system that we talked about are the capabilities were the Doppler signatures. I wanted to show you a real-life movie of a Doppler signature. The bottom plot is called a Doppler time intensity plot, and it measures all of the Doppler frequencies. This happens to be a human walking, and this human is first walking away from the radar and then coming toward the radar. The way that you read a Doppler time intensity plot is anything going away from you will appear on the left side of this blue chart. Anything that's walking towards you will be on the right side of the chart. And the further away from the center it is, the faster it's moving. So you notice that it's not a very clean signature here on this human that you're seeing there. And the reason for it is you're not only seeing the body signature, but you're seeing the arm and leg motions of that object. Well, the same way it is with drones. Drones, you'll see not only the motion of the drone itself, the main body, but you'll even see like appendages moving, the motors themselves, perhaps the shaft spinning. All of those features are features that you can exploit for drone characterization. This plot here is another example of drone, Doppler processing. This is a radar located near a road looking down a freeway. And what you're seeing here is all the vehicles driving down that freeway in one direction going away from me, in the other direction coming toward me on the opposite side. Sometimes within the system, you'll see some of these things seem to be moving in and out away from the rest of the groups. And those are actually cars that are slowing down or speeding up. You'll see the same kind of thing with a maneuvering drone. If a drone is coming towards you, it will have a nice steady movement on this graph. If it is maneuvering, its relative speed will change, and you will see it dance all over this graph. So that's one thing that you can tell with a radar. Even if the radar is just staring at the drone, we can tell whether or not that drone is moving, doing maneuvers or not, by just watching the Doppler image. Now, DMT has taken a lot of these types of capabilities that we just said. What are the things that you need? We've mapped these into a few of our radar systems. One of them is called the XRDS, shown here, and then the smaller version is called the Black Marlin. And the Black Marlin has the ability to look down 15 degrees, which may be needed if you're looking on a building, or look straight up. And this is really a nice feature for drones that happen to be coming directly at your facility and could be flying right overhead. You notice there's a camera on top, and any good radar system that you have should be able to help point some other object, like a camera or a jammer. And what I really like about this particular system is the fact that the camera system, in this case, can also match the same tilt angles as the radar. We also have done this before by mounting it on pickup trucks, again, tripods. We've done it on trailers. And these systems are pretty versatile. You can move them around. They're easy to set up. Again, it's something that you don't want to have a PhD to set these up, so the software should be pretty easy and straightforward. I have here a movie that shows us going on a data collection that we did in a nearby field. And what you're going to see here is you're going to see in the top left screen, these are the radar tracks being plotted on the user interface. You have in the middle here, this is the video coming from the camera located on the ground next to the radar. Then you'll see some of the other operator actions here and the drone's camera point of view in the upper right-hand side. So I'm just going to play this real quickly and you'll see what I mean here. It's different views and aspects to sort of show you from the perspective of the drone, from the radar, and from the operator viewpoints. The one thing we found out very quickly was for a camera, that camera needs to have an extremely good thermal image capability. It needs to see how small that dot is on the screen. I don't know if you can see it on your screens, but the dot was tiny. That was actually the drone at only about 300 meters away. So this camera is a $30,000 camera that can only see it for a few hundred meters away. So you need a substantially better thermal camera capability to see that drone at a much further distance. You can see it, the system up here tracking the drones. This is the end of the video. You can see the tracks of the drones as it flies here. You also see signal amplitudes. That was one of the things, remember I mentioned, was signal amplitude was one of the things it could do. And if you clicked on that icon, it would actually tell you what is its speed. You can also pull up the Doppler processing to see the actual micro capability. So we have a number of different radars that have that capability. And what I'd like to tell many of you is there's different capabilities out there for the various types of drone detection radars. Make sure you're matching what you want it to do, not force-fitting that radar to what you want it to do. So we have, for instance, some of our customers look at using two radars. One to really look at super long distances, and another to be able to catch those popping right up next to it at the fastest rates. And when you use two systems like that, I'll have to tell you the cost advantages are great. The more you try to make one radar do everything, the more likely it is you're going to have a disaster on your hands at some point in time. Inside the radars, you can see our radars have the ability, it says an elevation motor. This allows that radar to be able to tilt that antenna as it moves. Now you can also do this other ways, but like through electronic scanning. But in this particular case, this radar uses a motor to, as it's spinning in azimuth, it tilts that motor. So I'm going to move on to some more slides here that I have. Okay, so in integration, the one thing we've done is a lot of integration with with other camera companies. That's something that you need to be able to as cameras change, as your range requirements change, not every camera vendor has the camera you want. So you need to have the ability to look at quite a few different camera models, and these are just some of them that we do. Also, you want a full integration capability. We do these things called security bundles, and you may want to look at your radar vendors and ask them, do you have the ability to combine lots of the pieces together for me, like the camera, the suppression of lightning and surge protection, the ability to do network communications. Do you have the remote monitoring software capability? That's some of those things that you need to consider. Now, just to stay away a little bit from that marketing side, I just want to show you some of the key features on the command station that you might want. You want a map that shows the contact points of the radar. Now, our map system will also tell you the height of that above the ground. So as you are spinning, it'll also, if you click on it, says the height of that object is, 500 feet. The other things that it allows you to do is to see the signal magnitude. You can come over here if you're tracking more than one drone. You can actually see which one of the drones am I currently looking at and get more information from it, and having complete video window integration. I have another movie here just showing quickly some of this stuff in play. Here's the detection of a drone, and you can see here this camera on the right-hand side is trying to point the camera at the right drone, but the drone is so small that you can no longer see it in the video. It's actually surpassed the capability of the camera. But I just wanted to show you this is the kind of user interfaces that we have. Many of the competition and others out there have similar or use another third-party screen to show. So again, I'll show it here. There's the track of the drone, and then it turns around and comes back. And you can see the whole time that you can see signal strength and so forth as you go along. Okay, remember I mentioned about being able to get those points out there to others. We use what's called a web service in our radar system. This allows anybody who has any network capable programmer, anybody who can design a web page can actually build a monitoring program that can take our feeds. But We use the service to allow you to be able to ask at any point in time, what's my update? What's my update? What's my update? This sort of allows you to be able to, even on a low bandwidth communication capability, that you still can get the image updates. And you can also ask things like the microdoppler. In our case, the top screen up there is actually a true Doppler image of a type of drone. I'm not going to say which. And down below is someone from their browser has asked, can you please give me the image of that microdoppler? Well, you can catalog these images and yourself build filters that allow you to be able to characterize, well, maybe that's a, Maverick, or maybe it's, some other type of drone. You'll be able to determine that from the actual communication that you have with the radar system. So just to wrap up, the one thing that I wanted to say again is radar offers a fast, easy way to search for large volumes in the sky for drones. It can automatically queue other devices, which is really important, like cameras or jammers. It works in all weather as long as you selected the right frequency and Doppler processing. When you consider the volume of the sky that you have to search, radar is a cost-effective solution. If you were to try to do that with cameras, you'd have not a small fortune, but a large fortune placed in it if you had to do it with just cameras. And then the one thing I wanted to say to you is we have a lot more movies in our database that we have of drones, of us tracking drones, of actually different types of drones. So if you want some more information, please contact us. We have a lot of this stuff actually posted on YouTube and other web link sources, so you can get to us yourself. So if you need to contact me directly, I've put my email address here, and of course also telephone number if you need quotes or anything like that.